Yeah, you're trying to attend my class because I cannot guarantee every time I record my lecture successfully. And you also, if you have questions, you can submit your questions in the chat window, and so I can answer your questions. So today we're going to talk about the chain rule, but before we do that, I have to mention a couple things. First of all, remember if we have a single function, function with a single variable, right? There are several notations. This is called the derivative of the function with respect to x, okay? And this is going to be denoted by another notation, okay? And in calculus, this is also denoted by f prime x. But for functions with more than one variable, we're not going to use f prime, okay? And what is the definition? The definition of this is going to be x plus here f of x plus h minus f of x. Okay, so that's a definition. Okay. Then, okay, this is just a formula, right, for the function. So now, those are the notations. Okay. Now, if we have two variables, y and the x, they are related by this formula. Okay, if y is a variable depending on x by this formula, then we also have other notations. Okay, we can dy over dx is called the rate of change in y with respect to x. Okay, so what is it? What is that? This is another new quantity. Okay, and it depends on another new quantity. This is nothing but dy over dx. This is another quantity, but we use 4 letters to name it, called dy over dx. Just look at your name. Your name could be Johnson, right? Johnson. You have four letters, John, right? But you can also begin with John, and John is a name, right? And Johnson is another name. So we have it doesn't matter how many letters there. Okay, so this is actually is going to be this Okay, and it's also can be written in that form. Okay, so if you ask me what is dy over dx, and then if you are giving me the formula for the dependency of y on x, then I can give you some more details. Otherwise, it just leave like that. Okay, just dy over dx. Okay, so that's the review for the functions when variable notations we use. All right, now for a function of 2 variables, right? For the function with 2 variables, we also have this notation. This is we use instead of d, we use a partial. Okay, that's called when I differentiate this expression, f of x is an expression such like x squared plus y. Because this notation means I'm going to differentiate this expression with respect to x. Okay, and that is a notation also denoted by this. Okay, and in some book it's also denoted by this. Okay, those are the notations we use. And then the definition is similar. Okay, just x plus h y minus f of x. So you keep a y unchanged, then you change the x variable a little bit. Just view it as a function of x only, and keeping y in unchanged. Okay, so similarly you have this when you differentiate this with respect to y variable. Right, and you sometimes we denote by this notation, sometimes we denote by this notation. Okay, and then you have the limit. Right, then you have the limit. So this is a similar notation. Now, okay, here's the point. So if another variable called z, another quantity, and it depends on x and y. Okay, so that means if z depends on x and y, right? Then you can write down this equation, right? And f of x, y, it depends on the problem, so this is then we also have this notation, partial z with respect. Okay, so this notation, okay, is going to be this is a yeah, this is a sometimes we just simply write the partial differentiate with differentiate z with respect to x, okay, and then also it's simply written in this form, and yeah, similarly above we also have a what is this, right? So we we can also write in this, okay, and then dy over dx. Okay, this is a rate of change. Okay, similarly, the meaning of this is going to be the rate of change in z, okay, with respect to x, and then I put a little additional comments here. Keep y unchanged. Okay, keep y unchanged. Okay, so z depends on two variables. I just keep y unchanged, and then I differentiate and view it as a function of x. Okay, now how do you calculate, right? So this notation, what is that? If you want to know what is this, then this is it. This is nothing but this. Okay, it's also it's going to be this notation. So we already know how to find that. Okay, so this is a new quantity, partial z over partial x, partial derivative z of a partial, partial x, and that is a new quantity, and it depends on x and y also. And how do it depend? What is the formula? And the formula is here. Okay, so let's take a look at example. Okay, f of x or y is going to be x squared y plus, just plus y. Okay, plus y x cubed. Okay, doesn't matter how do you write. Okay, so if I want to differentiate this function, so I just differentiate with this expression with respect to x. So I get 2xy and 3x squared y, right? So we get this. Okay, so I can also say that this is a 2xy plus 3x squared y. Okay, so I get a new function. The new function, the name of the new function is called f sub x. Okay, so here's the function, the name of the function is f, and here's the name of the function x. I should put the sub x there. Okay, so sub x is the name of the function. Sub x of x to y is a formula for the function. Okay, so we should understand the concept. Okay, now here f is just the initial of a function, the word function. So you can use 3 letters to describe the function. Okay, it's not necessarily use one letter. You can use a combination of a letter, just like a password. Okay, you just a combination of the word and yeah. So for example, if I f1, okay, xy is going to be x squared y, right? Okay, and then f1 sub x is going to be 2xy. Okay, so if you have more than one function there, you really have to use more letters or numbers to describe the function. Okay, just like a name, in the world, if you only have one person, you don't need to use too many the combination of too many letters, right? It's just A, right? Okay, Mr. A. So A is just one. It's one name. If you have that more than 12, then you need 12 letters, more than 12 people there. But yeah. So this is locally in the past. Okay, we don't have internet. All the data is not connected. So,
hey Professor, why do you have 3x squared there? Was it originally it was a 3
function? No, I have x squared x cubed, and when differentiate, I get 3x.
My fault. I wrote it down as squared.
It's okay. Yeah. So I just say why we have to use more than one letter to name the function. Okay. So this is our notation. Then okay, if z depends on x, okay, depends on x and this is x squared y, right? Okay, for example. So I do not mention the f here. Okay, just direct it right now. Actually, x squared y is a formula for the function. Okay, then partial z partial x is a new variable, that'll be 2xy. So yeah, when you get used to that, So this is yeah, it's just just differentiate x squared y with respect to x. Okay. Now you can also continue to differentiate this one, the second second derivative, a second partial derivative, and actually is going to be a partial derivative of this. Okay, you differentiate the derivative again with respect to x, so that will be just 2y. Okay, just differentiate about expression with respect to x. Okay. And so you have a quantity, three quantities, x, y, z, and z depends on x, y. Then you get a new quantity called partial z over partial x, and that depends on, it also depends on x, y, and by the formula, this equals 2xy. Then you differentiate again, differentiate above quantity again with respect to x, is the new notation with partial square z over partial x squared. Okay, then this only depends on y now. Okay, x is gone. Okay, those are the notations. Okay. Now here's our key point. Okay. If we okay. Okay, so here's if z depends on x and y, okay, and x, both x and y depend on another variable that's called t, right? Then clearly z depends on t, right? Right? So because z depends on x and y, and x and y depend on t, then z depends on t. So z is a function of t. So you can talk about rate of change of z with respect to t. Okay. So z is the only function of t right now. Okay. So you can use a notation at dz of dt. Okay. You can, I don't use a partial because z only depends on t, no as a variable right now. Yeah. The final result will be z depends on t only. All right. So now, yeah, how do you understand this? I can draw the picture. Suppose, yeah, I'm parallel, okay? So z depends on x and y, so you can express in this form. Now x depends on t, y depends on t, then z is gonna be f, x of t, y over t, so that is a function of t, okay? Right? So it's much clearer to see that z depends on t. So you can talk about the derivative of z with respect to t. How can I, yeah, so the Chero says that it is going to be the derivative of z with respect to x, then the derivative of x with respect to t, because x depends on t only, so that's I use d instead of partial. Then don't forget the partial derivative of z with respect to y and the dy over dt. So this is the Chero, and there's a two. Okay, it's different from the channel we learned before. You have only one middleman. Okay, so right now the picture looks like that. Here z, okay, z. Then the next level will be x, y, but the both depends on t. So that's a relationship. So that's why when you differentiate z with respect to t, you have to differentiate z with respect to x. Also differentiate z with respect to y. Okay, so that and then you can find a formula for the derivative with respect to t. Okay, this is like the organization of some company. There's one person on the top, and then they have two managers under that, then only one one employee. Okay, so only one variable here. So you want to find the relationship. This is a this is a channel. It's easy to understand, but if you have many variables in the middle, don't forget to differentiate the quantity with respect to all those variables. That's all we needed to learn today. Okay, this is the only form. Now, if z is already have a function here, z is equal to f. I know partial z with partial x can be replaced by f. So there's other formulas you can explain here. partial z of phi x can be replaced by f. Okay, so that's the same. Okay, because I already said that if yeah, go back to our notation, if z, let's go back here. See, what is my notation? Yeah, so here's the notation. So there's no difference, yeah, partial z or pi, if z is equal to f of x, then this is given by the formula. But what I did here is I did not mention x and y because it's too complicated. Okay, so I just ignore x and y. So more precisely, I should write to like this. Okay, if I use the f to replace it. Okay, but for simplicity, I do not write as a parenthesis x comma y. Okay, yeah, because the notation for this, yeah, you need a variable x y there. Okay, so yeah, you can compare both sides. For I think it's better if you don't want to mention the f, then this is the chain rule we needed to learn. Okay, this is the chain rule we needed to learn. Yeah. Okay. Now there's yeah, let's do some exercise, then we understand this better. Okay. Let's go to the book and find some exercise. Okay, so here's a problem. I'm going to get z depends on x and y, and x is going to be tangent t. Okay, y is going to be arc tangent t. Okay, so we want, so then z depends on, z depends on t, right? So I want to find out dz dt. Okay, there are a couple ways to do. You can do it directly, or you can do it separate. Okay, you can do directly because z is going to be indeed as a function of this will be arctangent to t. So z is a function of t. So you can find the derivative. But we can use a chain rule to solve the problem. Okay, so that is going to be partial z with respect to x dx dt plus partial z partial x partial y. Yeah. Okay. So look at this. We need
is this really the chain rule, or is it really more like the product rule?
Yeah, this is.
It feels like it's like the partial derivative of one times the derivative of the second.
It's a chain rule. It's a chain rule. But yeah. But there's a two middlemen here, x and y. So that's why you have to take care of both of them. That's why you have to differential z with respect to x. Then don't forget differential z with respect to y. Okay. Yeah. So this and why you have the sum of the two terms, because there's two variables in the middle. Okay, two variables in the middle. Okay, two variables in the middle. That's why you have to take care of all the variables. Okay, now we can prove that why this form is true, but our main focus is not a proof here. So, in the book, yeah, indeed, there's I think there's an argument proof shows you why this is true. Okay, you have to have this is not product rule. Okay, this is not product rule. It's a
I believe you. I believe the proofs. We've known it for like 500 years since calculus was discovered.
That's right.
That's good enough for me.
Calculus is not 500 years. Calculus maybe, I don't know, what's the first? From Newton's time, yeah. So yep, I don't know how it is. Yeah, calculus is, back to Newton. Yeah, maybe 300 years ago. Okay.
Yeah, something like so that, 1700s, yeah.
Yeah, so this is 1 plus xy and 1/2. So let's find out this partial derivative. It's going to be 1/2, 1 plus xy, and negative, and then differentiate xy with respect to x, so that's y variable. Okay. And similarly, so when you do the homework, you write down the formula first, and this is how do you to follow, so you make it clearly. So even you make mistakes on one of the derivatives, if you express it clearly, then you get most of the credits. Otherwise, if you just give me the answer and skip a lot of steps, I cannot tell how did you solve the problem, then it's very hard for me to give you partial credit. Okay, so this is the partial derivative. I also have to find the derivative, and the derivative is going to be a derivative of x with respect to t. Now, do you remember the derivative of this? I think it's tangent square t, right? Secant square t. Okay, if you forgot, if you only memorize the formula for the derivative of tan sine t and cosine t, and you can derive it. Okay, this will be just a square one over of a cosine square t, so that's called secant. And the derivative y with respect to t, that's the inverse function. Inverse function, yeah, you do need to memorize it. So 1 over 1 plus t squared. Okay, so you write down all the required derivatives, okay, for the above expression. Then your conclusion is you just write here half of y, and I think you don't need to put the details here. Y, yeah, this is negative 1/2, and here secant square t, and plus, okay, half of x, it's a 1 plus xy, negative 1/2, and the 1 plus t, okay? And I think that's good enough. Yeah, you can say where x is going to be tangent t, y equals arctangent t. Because if you cannot simplify, there's no need to put tangent t and arctangent t into the expression. Okay. Okay, so that's very yeah, it's clear enough to me. Okay, sometimes you do need to replace x and y. Okay, this is not a good problem. Let's try another one. Yeah. Okay, let's try another one. So here z is going to be x cube y, yeah, minus xy cube. Okay, now x is going to be t squared. Okay, y is going to be 1 plus t cubed. Okay, so something like that. So we want to find out the derivative of z with respect to this time. Maybe you have to put all the details. Okay, so you get a function for t. Now z is a function of t because if you replace x by t squared and replace y by 1 plus t cubed, it's a very complicated polynomial. Okay, so our yeah, what I'm going to do is here. So I write down the formula. Okay. Now you may skip some steps. You don't need to separate to write down the formula for the partial z with respect to x, partial derivative with respect to x. You can directly put the derivative there. So differentiate this above term with respect to x. I get 3x squared y minus y cubed. Okay. Then I differentiate x with respect to t will be 2t. And then the next term, the derivative of z with respect to y, so will be x cubed minus 3xy squared. Okay. Then the derivative of y with respect to t will be 3t squared. Okay. So this is almost the answer, but we can also, it's harder to, I said it's harder to simplify. Okay. What I'm going to do, you can take a y out, right? You can take an x out, both sides, but take the y out. Yeah, I don't think we are, if you use a maple, can quickly simplify. Otherwise, I'm going to leave like that. Okay, so t is x squared, y is 1 plus t cubed. Okay, and if you want to put the details, it's a little more complicated. So 3t squared and the square is t to the 4th power, 1 plus t cubed minus 1 plus t cubed, and then 2t and plus, and t to the power 6 minus 3t squared, 1 plus t cubed and square, and 3t squared. Now, it's indeed a polynomial. Yes, you can write on polynomial because if you know the formula 1 plus t cubed and the cube. Okay. Okay. Now let's take a look at another case. And here z depends on, z depends on x and y, okay? But x also depends on s and t, the two variables. Y depends on s and t. So here's a diagram, okay? Here's a z. Z depends on x and y, but both x and y depends on s and t, okay? So now z depends on s and t. Z becomes a function of t, right? Then, so then z depends on s and t. So it's a function of s and t. So z is a function of st. So you can talk about partial derivative z with respect to s, partial derivative z with respect to t. Okay, what is a chain rule? Okay, you have two middlemans in between them. Okay, the dependency of z on s and t is not direct. So you insert two middlemans here, right? The middleman. Okay, so you can only write partial z with respect to x, right? But when you differentiate this, it's the same. You can write the formula, right? So you have to take care of the x and y first. Partial z with partial x. But this time, you differentiate x with respect to s only, okay? And then partial z with partial z, partial y, and here it's a y and s, okay? Okay. So it's very similar. Just view t as a constant. That's it. View t as a constant when you differentiate z with respect to s. Okay, but here our notation must be partial x or partial s because x depends on s and t. It's partial derivatives. That's the only difference. Then similarly, you will have this formula. Okay, so that will be two partial derivatives. And this is a chain rule. Right? This is a chain rule. Right. Right, now let's take a look at next problem. Okay, we have z equals square root x, e to the x times y. Okay, and here x is 1 plus st, y is going to be s squared minus t squared. Okay. So z is a function of s and t. Now, if you want to put the detail there, so this will be 1 plus st and e to the 1 plus st, then s squared minus t squared. So z is indeed a function of st, right? Okay. But it's a pretty complicated expression. And when you study, you can find the derivative directly. And find the derivative, partial derivative of z with respect to s. So what I'm going to do is, I'm going to find the partial derivative with respect to s, use a chain rule, okay? So I will, first of all, get this, right? Okay. Then we do step by step. So this, the partial derivative of z with respect to s. I think I can use I can use a product to solve this problem. Okay. So the derivative of z with respect to x, the partial derivative, so the product through the first one, you have to differentiate square x. So you get this, right? Then when you differentiate the second term, I think I get a y. Yeah, so that's what I get. And then partial derivative of x with respect to s is going to be, I get t here because it's
Professor, would you mind doing this in the where we found each component and then plugged it in formatting?
Yeah.
Because you could do this in your head, which is great, but I cannot.
All right. So I would after finish that, let me break it to several steps. Okay.
Sure, that's fine.
So, then I differentiate z with respect to y, and I don't need to use I don't need to use a product rule here. It's just y e to the xy. Okay. Then I differentiate y with respect to s. That is 2s. Okay. So this part. So let's do step by step. Okay. First of all, you write down this formula. Then you have to calculate each of them. So this will be the partial derivative of what is a z? What is a z? Yeah, z is a square of x e to the x times 1. Okay. So when you differentiate this with respect to x, you see there's two terms there. Right? It's a product of two terms. Each of them contain x. So you have to apply the product rule. Okay. So apply the product rule, keeping x, y as a constant. So that's why product rule tells you the derivative of square x with respect to x is this. And then, okay, then you have to differentiate the second term with respect to x. Y is a constant. That's why it's e to the y to times e to the x times y. Okay. So that is a product rule here. Okay. And then you needed to calculate the derivative z with respect to y variable. When you look at this expression, that y variable shows up only in one place. So square x is independent y variable, so you can view it as a constant with respect to y variable. So that's why you can, one more step, right? Then you just differentiate this with respect to y. So x is a constant, so you move down x. Okay. Yeah, move x down to the front of this. All right, to the function. So then, this is how do we get the second term, right? Then the partial derivative of x with respect to s, and this is 1 plus st. So when you differentiate, the first term is 0. The second term, okay, t is left, right? Because it's product st. Right? Then the partial derivative y with respect to s, and what is that? S squared minus t squared. So t squared is independent of s, and it's constant, it's a 0. So the first term is 2s minus 0. Okay, that's just 2s. This is the t. So you plug them into the above formula, then you get all the terms. Right? I think, my opinion is you don't need to replace x and y by the given formula 1 plus st and s squared minus t, because otherwise it's just expression more complicated. So it's very clear to me now. You solve the problem. The answer is almost ready. So this is this is how do we do the problem. Okay.
Thank you. That was very helpful. That's exactly what I needed. Thank you.
Yeah, that's right. So here I show you how to get all the steps. So now okay, let's do some story problems. There are some other problems we need to work out. Okay, and let me try to find. Okay, so there's problem number 14 in the book. We should know. Okay, we RST is given by, this is a composite of two functions. okay? And we know that u, when the 2's value is going to be 5, u, and when the 2, the derivative with respect to s is going to be 4, ut, the derivative with respect to t is going to be -3, and the v, the value at when 2 is 7, vs, that will be 2 vt at that point is going to be 6. Okay. We also should know the derivative of u with respect to u is going to be 9. Yeah. We're not given the formula of each function here. We only given the specific value of those functions at the special points. Okay. What we want to find out is find the r, s, and the when the t. Okay. So I think this is not a difficult problem. Just all you needed to write down the formula for the write down the formula using the chain rule. Okay. So the formula using chain rule here is s. Okay. Without mentioning the variable, this is a rs, right? But that's a partial derivative. How can I? Yeah. Let me Let me use as a notation. Okay, so I'm going to differentiate r of st with respect to s. Okay, this is this by the chain rule, you have to differentiate g, right? Yeah, this is this is notation is r st. Okay, so by the chain rule, I'm going to differentiate g with respect to u, okay, and the partial derivative with respect u with respect to s. Okay, so if you want to put more details there, this will be g u s t. I'm sorry for this. Yeah, this is a channel st vst, right? And then the partial derivative. This I'm going to use as a notation u sub s. Okay, and then the second term will be gv u s t v s t v s s t. Okay, so this is a detail formula. Okay, now if you plug 1 and for s, yeah, when s equals 1, t equals 2, right? And the r, s, 1, 2, you can calculate. In this case, u 1, 2 is going to be 5, right? Remember, u and v, when the value of v at 1, 2 is going to be is 9, yeah, or 7, sorry, 7, 5, 7. So this just equal to 5 and 7, okay, us 1 2, and gv 5 and 7, and vs 1 2. So then you go back to the given information here. Here's a list of the table, right? So all I have to do is just plug the numbers for them. So g sub u is going to be 9. U sub e, that's going to be 4. G sub v is going to be -2. V sub s is going to be 2. Okay, so that's it. Now this is a 36 minus 4 will be 32. So the variable is 32. We don't need to know, we actually are not given the detailed formula for u s of t and v s of t. Okay, and even we don't know the function for capital G. But we only needed this information in order to find the derivative for R with respect to t at that particular point. At this particular point. Right. Okay. So here's another problem I want to talk about. Right. If u is going to be x to the fourth power y plus y squared z cubed, okay, where x is going to be RSE to the t, okay, y is going to be R s squared e to the negative t. And the z is going to be r squared s sine t. Now, find the partial derivative of u with respect to s when I equals 2, s equals 1, t equals 0. So let's understand this problem. Now, actually, this is a function of z depends on three functions here. Z depends on three variables, x, y, z. I did not mention that formula if it depends on three variables, but the channel is similar. Okay, let's draw the diagram. So z depends on x, y, and z. Okay, and then you have r, s, t. So each of the variable depends on x, y, z, right? So now z is a function of RST. How can I write down the channel? That's very similar, okay? You have to go through all the three minimums, x, y, z, in order to reach the IST. So partial, write down the formula first. And this will be the partial with respect to x. Then this is the first term. So you should have three terms here. Okay, so this is the formula you're going to use. Right. If there's only two intermediate variables, then you only have two terms. You have three variables, x, y, z, then you have to use, you have to have three terms. You have more than three, you have four variables in the middle between z and the RST. Then you should have four terms, yes.
What is that last, second to last term there, the partial derivative of some value over z? Not that one, the other one.
Yeah, that's u. Yeah. Is a u, okay?
A u? Okay.
Yeah.
Thank you.
It's the same u, you see, identical, just changes the variable x, y, z, okay?
Okay.
It's the three terms. Right, and okay, using this formula, then you have to calculate each of them, and the question is, how do you do that? If you don't use a chain rule, okay, and you needed to plug all those expressions in for x, y, z into the above expression. So then you get a formula for u expressed in terms of SIST, but we don't need to do that, okay? So what I have to do, we have to do some calculation, okay? When I equals 2, s equals 1, t equals 0, and what is my x? My x is going to be I is 2, s is 1, so 2 times 1, e to the 0, so it's 2. Y is going to be I is 2, S is 1, e to the, this is negative t, right? Negative 2. So it's going to be negative 0, so it's still 2. Z is going to be 2 square, 1 sine t, t0, right? So that's 0. So 2, 2, 0, right? At that point, the value of x, y, z would be 2, 2, 0. Right? So now I have to calculate each of the terms. So partial x. Let me write down the formula here, and the u equal x to the fourth 1 plus y squared z cubed, right? So z cubed, yeah. So I'm going to differentiate with respect to x. I get 4 x cubed y. That's it. And the u, the partial derivative with respect to y variable, I get x to the fourth plus 2y z cubed. Okay, and then the partial derivative with respect to z, I only get to the last term, 3y squared z squared. Okay, yeah, so those are the 3 terms. Okay, what else? Oh, I have to find the partial derivative x with respect to s. Okay, partial derivative x with respect to s. So remember, this is about formula. I have to look at on the top. So this is a derivative with respect to s, so it's I to the t. And that is a derivative with respect to s, that's a 2rs e to the negative t. Okay, and that's r squared sine t, okay? So now we have to evaluate each of them. Okay. So when r equals 2, s equals 1, t equals 0, x equals 2, y equals 2, z equals 0, and the above derivative have a special values, okay? So you can, you can check that. How can I do? So I can write down all the values, okay? When I equals 2, s equals 1, t equals 0, x equals 2, y equals 2, z equals 0. So the above derivative is going to be, I just use x, y, z here, so that'll be 4 times 2 cubed, y is 2. So that is going to be what? 64, I think, yeah. That would be 64 because, yeah, 8 squared, so 64, okay? Partial u, partial y, and that is going to be 2 to the fourth power, and 2 times 2, z is going to be 0, so just 16, okay? The last term is going to be 0, because z is 0, 3 times 2 squared, 0 squared is 0. Yeah, just step by step. When you calculate this partial derivative, when I equals 2 is 2, e to the 0, that's 2. Partial derivative of y with respect to s, and that'll be 2 times 2 times 2. Hold on. 2 times rs. Yeah, s is 1. Okay, so it's 1. E to the negative 0, and that is going to be 4. Okay. I think the last term is going to be 0 because sine, it's going to be 2 squared sine 0, so it's 0. Okay. So you got all the values, and then we get this. Okay. And then you go back to this. Just basic is a product, 64 times 2, and this product 16 times 4, and 0 times 0. Okay. And then you simplify it. Okay. And then you get the answer. Okay. It's a little bit complicated, but basically just break down all the the computation into several steps. Okay. Now, if you want to differentiate directly, it's possible, but it's more complicated the derivative. Okay. So I suggest you to use a chain rule to solve this problem. If it's required to use a chain rule to solve this problem, you have to use a chain rule to solve this. Okay. Right. Now I'm going to talk about implicit differentiation. Okay, sorry, I didn't do this. Right, and if you let's begin with the first two. Okay, so you're given two variables, right? X and Y. The relationship between X and Y could be simple. Sometimes the Y equals, Y depends on X, X depends on Y. But sometimes the dependency is not given explicitly. Okay, so Y depends on X, okay, by any relationship, something like that, okay, something like that. It may be a constant, but it's okay. Yeah, something like that. Instead of Y equals f of X, okay. Remember, yeah, if we have this is a better way. So Y depends on X by the formula Y equals fx. We are familiar with that. That's the easy one. That easy dependence. But here is a dependency is complicated. You cannot solve for Y in some cases. For example, like 1 plus x y and plus 3y to the fifth. Can you solve for Y in the X? No. Okay. So this is you cannot express Y in terms of X. Okay. Explicitly using elementary function. Okay. So there are some reason you cannot do that. Okay. So x, y depends on x, y depend y depends on x. Actually, also x depends on y. The dependence of x on y is much easier to understand. Okay, but depending on y on x is much more difficult. Okay, so if I want to find x, I can do that. I move -1, -3y to the fifth to the left, and divide by y, right? So x depends on y. Okay, clear. But the y depends on x, and you don't know. Okay, it's impossible to solve y in terms of x. You cannot express the y in terms of x using elementary function. Okay. So sometimes there's no way to give explicit expressions using elementary functions for the dependency. Right? So it's not always like this ideal case y equals f of x. But how do I find the derivative? How do I find the derivative of y with respect to x? Okay, implicit differentiation. Remember, so it's only two variables. Okay, so you can differentiate with respect to x, right? And then the derivative is going to be both a zero. This side is zero. So when I differentiate a function with two variables, and this is just use a chain rule, okay? That's a derivative with respect to x. So this notation can be written in the form, and that's a derivative. The chain rule says that. Okay. This is a dx. Okay. The variable is just x. Partial derivative y. All right. So dx over dx is going to be 1. So therefore, you have that is what actually what we learned before in a chain rule. Okay, right now with a partial derivative, I can solve for that. I move this term to the right hand side. I get negative sign. Okay, then I divide both sides by the partial derivative y with respect to x. Okay, and sometimes just simply return as, yeah, if you don't want to mention x, y, then that's okay, for simplicity, okay? There are many notations. This is called f sub x, y. Okay. And sometimes you can ignore x, in the formula. So this is a formula, actually. Okay. This is a formula. You can also have more than one variables. Okay, and similarly, you can have solve the problem using more than one variables. Okay, for example, if we have a x, y, z, right, related by f capital X, Y, Z, okay, by this equation, then you can say x depends on y, z, y depends on x, z, z depends on x, y, of course, right? They all depend on each other. They're bounded together. So we assume, yeah, z is sometimes sometimes we can express z in terms of x, y. Okay? Sometimes you cannot get express differentiation. Okay. Yeah, this may be, question is whether you can express z as a function of x, y. Okay, so what I'm going to do is I'm going to differentiate. So z, if z depends on x, y, I can talk about the partial derivative, right? Yeah, this is supposed to be 0, right? So when I differentiate f with respect to x, then actually is going to be 1. So I already have this is going 1 because the partial derivative of x with respect to 1. Right, then I differentiate this with respect to y. Okay. Okay, x, y, no, y is independent of x here, okay? Because here you view z as a function of y. So the second term is going to be 0, okay? And then the third term, okay. So similarly, you will get the formula. The partial derivative of z with respect to x is going to be negative. And the term on the top, we move it to the other side. You have a negative sign and divide by. Okay. Okay. So you can also similarly, yeah, you can also get the partial z with respect to y variable, and you have a y z, and this is z, okay? And here, okay. So that's a very similar idea, just like in the first case. Okay. So those are you can find the partial derivatives of one variable with respect to other two variables. All right, let's take a look at. Okay, let's take a look at the example. Okay, where's my 5? Okay. Right, so the following problem is familiar. You know, we did it in calculus 160. Yeah, 160. 65, 66, yeah, 65, calculus one variable. So given the relationship x cubed plus y cubed equals 6 and 1, okay? Find the partial derivative of y with respect to x.
Sorry, what's that term? Is that 6xy?
6 times xy, yeah. Yeah, 6xy. Yeah, so this is a 6xy. Yeah, let me write this. Okay. All right, so forget the multivariate calculus. Now we just this is a problem we did before. Okay, how did you do that? We just differentiate both sides with respect to x, right? Then use a chain rule because the derivative of x cubed with respect to x will be 3x squared. But the derivative y cubed with respect to x, you have to say y squared, and don't forget the partial the derivative of y with respect to x, right? Because y is y depends on x, and here you have to use a product rule. It's a 6 times the derivative of x with respect to x is 1, so it's y, and then 6x, then dy dx. Okay, and so we solve for the derivatives. Okay, so you get 3y squared dy dx. You move all the terms together. Yeah, I like terms together. Yeah, you move 3x squared to the right hand side. Then you factor it. Okay, then you divide both sides by 3y squared minus 6x. You get the answer. Okay, now doing that, I find out that some students always make mistakes. The reason is they are sometimes forgot to differentiate, you know, like a y cube, when you differentiate with respect to x, is forgot to put the derivative y with respect to x. Then this term is viewed as something without the derivative, just 3y squared. Then the answer would be wrong. Okay, this is the tradition what we do without using function of two variables. Okay, what I'm trying to do is rewrite this equation. Okay, I write it in the following way. Okay, this is a same equation. So now my function f of x is going to be x cubed plus y cubed minus 6y. Okay. Then you can use a formula to find it, right? So we know that the dy over dx is going to be negative fx, right? And y, and fy x y. That's what we have. Yeah, we already derived the formula. So all I have to do is just find the partial derivative of f with respect to x, the partial derivative of f with respect to y variable. So let's find the partial derivative. All right, so partial derivative of f with respect to x, so you differentiate each term with respect to x. I get 3x squared and plus 0 minus 6y, okay? That's the first term. Then I differentiate with respect to y, so 3y squared minus 6x. Right, then you plug into the above formula, I find the derivative. It's pretty fast. I will not miss any terms. So 3x squared minus 6y, 3y squared minus 6x. Right, I think I get exactly the same answer. Of course, I have a negative sign in front of that, but if you look at the above, Yes, if you can take a negative sign out, so it's 3x squared minus 6y and 3y squared minus 6x. It's exactly the same answer. Okay. So yeah. Let's try another one. So the next problem is here x cubed plus y cubed z cubed plus 6xyz equals 1. Okay, we want to find out the partial derivative of z with respect to x. And of course, this is going to be expressed in terms of xyz. So xyz are related by this equation. So technically, theoretically, you can express z in terms of x and y, but we cannot get the formula. Okay, so no way we can differentiate f of x, y in order to find the derivative of z with respect to x. Okay, so what I'm going to do is I'm going to direct, I can use a chain rule, right? So you can differentiate, you can do the, let me use a formula first, okay? So the above equation can be written in the form like that. So I let capital F x y z to be x cubed plus y cubed, z cubed plus x y z and minus 1. Okay, I move 1 to the left hand side. So the above equation becomes this equation. Okay, just 0. Okay. So we know that we already get, then we get partial z. Okay, this is x is going to be negative. Remember, that's it. That's what you get, right? So you write on this first. Then all I need is to find the partial derivatives of this capital F. So when I differentiate with respect to x, I get 3x squared. The second term is 0. The third term is 0. The fourth term will be 6yz and minus 0. So it's 3x squared plus 6yz. Okay. Then I find the partial derivative with respect to z. I get 0 plus 0 plus 3z squared plus 6xy and minus 0. So it's 3z squared plus 6y. All right, now just plug them into the formula. Then you get the partial derivative z with respect to x. Okay. So this is a partial derivative. But you can also do the following thing directly. Okay. So you can let's go back to the equation. I have x cubed plus y cubed z cubed plus xyz equals 1. How can I differentiate directly? So I put partial derivative, this operate, okay, on the both sides of the equation. You don't need to modify the equation. Oh, wait, okay. You don't need to modify the equation. This is a z cubed plus 6xyz. Okay, remember that, okay, two things. Okay, here's a note, okay. Y is independent of x, okay? So that means the partial derivative y with respect to x should be 0. Okay? And z depends on x. Okay? So this is the two things you have to keep in mind. Okay, now you differentiate both sides. Okay, so the derivative, partial derivative x cubed with respect to x will be 3x squared. And the derivative of y cubed with respect to x will be 0. The derivative of z cubed with respect to x will be 3z squared, but don't forget you have to put the partial derivative of z with respect to x. And similarly, in the 6xy, this you have to use the product rule, right? Yeah, the product, and the y is a constant, so it's 6y. Taken out, then the derivative of x with respect to x is 1. The derivative of x, then you have this. So that's a product rule, right? Y is a constant, and that is it. Okay. And if you're able to do this, then you can solve the problem. Okay, let's write down 3x squared plus 3z squared plus 6yz plus 6xy. And you have two terms the same, continuous the partial derivative of z with respect to x. So, so what I'm going to do is I keep those terms on the left-hand side and move the other terms to the right-hand side. Okay. Then I solve this equation. I get this. I think you can simplify a little bit. Divide the numerator and denominator by 3. So you get x squared plus 2yz, and here z squared plus 2xy. I'm not sure we get the same answer. Let's double check, okay? Let's double check. Yes, the same. I didn't even simplify it here. Okay, so yeah, after you simplify, 3 should be gone. Okay. All right, so that's it for today's class.